rules for binary addition, we should take a note that 1 plus 1 equals 1, 0. The sum is 0, and the carry out is 1. Carry out is 1. We should know. And when on input carry equals 1, the rules are one plus 1 plus 0 equals 1, 0. So 1 plus 0 plus 1 equals 1, 0. And 1 plus 1 plus 1 equals 1, 1. Equals 1, 1.
So we finished last time this one. Binary addition, subtraction, and multiplication.
Yes, this is wrong. This is wrong. It is 1, 1. The sum is 1, and the carry also is 1. This is the binary rule. Addition rules. And the binary subtraction rules are like decimal subtraction. 0 sub 0 equals 0. 1 sub 1 equals 0. 1 sub 0 equals 1. Other 1, 0. In fact, it is 0 sub 1. 0 sub 1 equals 1 because he has borrowed 1 from the nearby position. So we should know that the subtraction is also like decimal subtraction, and we can convert the binary number to decimal number and then use decimal subtraction rules to get the binary subtraction result. And binary multiplication. We only need to know that 1 times 1 equals 1, and the others are 0. The binary multiplications, this is 2 bits binary number multiplication, and this is 3 bits binary multiplication. The rules are also the same, are all the same. Division. In fact, the computer can do the division. Using multiplication. Using multiplication. So we don't need to understand this rules very much, and we only need to know binary multiplication. And section 2.5 complement, for one's complement and two's complement. The one's complement of a binary number is the number that is formed by reversing all the digits. To form the one's complement, change all zeros to ones and all ones to zeros. But for positive number, we don't need to convert the ones complement. Positive numbers ones complement is itself. You know, only negative numbers has ones complement. Negative number its one's complement need to reversing all the digits. So for positive number, for example, positive number 34, positive 34. Its one's complement is 34. Is for all we use 8 bits, 8 binary bits to represent 34. Is how to write binary number? The binary number of 34.
Thank you. Bit binary sir. 0010
0 0 1 0
0010
0 0 1 0.
Yes. 1 2 3 4 5. 2 4 5 32 and
No.
yes sir.
0 0 0 1.
Sir, 34 equals 32 plus
2 plus
32.
Yes.
So 2 power 5 plus 2.
Yes. We use the rules.
2
1 0 0
1
8
1
1
0
0 0 0 1. So the result is 1 2 3 4 5 6 here.
So
0 0 1 0 0 0
Yes.
Yes. Okay. So the binary number is 0 0 1 0 0 0 1 0, and the one's complement of this number is also 0 0 1 0 0 0 1 0, because it is a positive number. Where is the eraser? Eraser.
sir, yes sir, there is someone take this from this class.
Okay, thank you. So the one's complement of this number is also 0 0 1 0 0 1 0, because it is a positive number. But from negative number. For example, minus 3, 4. Minus 3, 4. 8 we use other number to represent this number is also 0, 0, 1, 0, 0, 0, 1, 0. And then the ones complement of this number is 1, 1, 0, 1, 1, 1, 0, 1. In the computer, we use this number to represent minus 34.
This
This is 1, 2, 3, 4, 32 bits. 32 bits. We use 8 bits. If we use 32 bits, also it is also the ones complement of this number. So, and the last bit is the sign bit, and also the last bit of this is also the sign bit. If we use 16 bits, the number is 0, 0, 0, 0, 0, 0, 0, 0. 0, 0, 1, 0, 0, 0, 1, 0. And the ones complement is 1, 1, 1, 1, 1, 1, 1, 1. You know?
Yes.
And 1, 1, 0, 1, 1, 1, 0, 1. Like this. This is the one complement, and the two complement is plus 1, right? The tooth complement is 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, right? Calculate on your calculator. This is 1, 1, 1, 0.
Yes.
Because in computer, in calculator, we use two's complement to represent minus number, to represent the negative number.
Yes, sir. This is
Right? Yes. Yes. Yes.
but sir, my question is here. For this positive number, the first complement is the same. Yeah? 0, 0, 1, 1, 0, 0,
Yes.
0.
Yes.
So this for plus 34, so positive, the first complement is same. Yeah?
What?
For positive number,
Yes. Positive
the
number.
first complement is same.
Yes.
But for negative number, we get from this positive
Very funny.
minus 34. We get from plus 34, 0, 0, 1, 0,
Yeah.
0, 0. So the first complement
Yes.
is 1, 1, 0, 1, 1, 1, 0, 1.
Yes.
So second
The second tooth complement
plus 1,
plus 1.
so 0, 1, 1, 1, 1, 0, 1.
Yes. Yes.
34 plus 34, first complement, second
The
complement
second one is also the same.
plus 1.
It's also the same.
Why?
We don't need to use ones or two's complement to represent the positive number.
So 39 is binary. So plus 39 is 0, 0, 1 0 0 1 1 1. For this one, this is our sign bit, this is first complement, this is also second complement. Yes? We don't need to add this.
We don't need to use ones or twos complement to represent positive number.
Also, this is 0, so this is positive number.
Yes.
Thank you, sir.
Ones complement and twos complement. Twos complement is by adding 1 to the LSB of the ones complement. We should know that. We should know that the sign bit for positive number, the sign bit is 0, and for negative number, the sign bit is 1. Is 1. So when we want to find all numbers, ones complement or twos complement, we should remember that the highest bit, the HSB is our sign bit, So when the number is a positive number, the sign bit is 0. And when the number is a negative number, the sign bit is 1. We should remember. Sign binary numbers. We use MSB to represent the highest number. The highest bit is the sign bit, and LSB is the lowest bit. Please note this. Take a note for this sentence. Computers use or modify twos complement for sign numbers. Positive numbers are stored in true form, with a 0 for the sign bit. You said for this, take a note for this sentence. In computers, positive numbers are stored in true form, with a 0 for the sign bit. So we don't need to use ones or twos complement to represent positive numbers. Only negative numbers. Only negative numbers are stored in incomplete form. With a 1 for the sign bit. You can find this sentence in page 25. Page 25, the if note. On page 25, there are some bordered sentences. They are very important.
20.
Page 20, page 25. Page 25. Yes, this sentence, this one, and this one, and this one. Yes, yes, they are very important. Yeah, positive, zero, yeah. Yeah.
So minus 19.
Yeah.
So this is minus 19. This positive value.
Yes.
First complement is 0.
Yes.
So
Yeah.
complement. So
Yeah.
this is negative. So this is negative.
Yes. Okay. Floating point numbers are a little complex. Arithmetic operations with signed numbers. Is also like decimal arithmetic operations. We only need to take a note that the last carry should be discarded. The last carry, because the MSB is on sign bit, so we don't need to use the carry out of this sign bit. We should know that if the number of bits required for the answer is exceeded, overflow will occur. Overflow. For example, for these two examples, the number is 128 plus 129. The result cannot be represented by 8 bits. Cannot be represented by 8 bits. We use 8 bits. The value should be minus 127 to 28. If we only use 8 bits to represent all binary numbers, the minus value is minus the minimum number value is minus 127, and the maximum value is 128. If the result exceeded this value, the result will overflow. Overflow will occur because minus 128 is less than minus 127. So the result is wrong. also we also cannot use minus 127 plus minus 127 because the result exceed the minimum number of 8 bits. And this occurs only if both numbers have the same sign. The overflow is indicated by an incorrect sign bit. So, how to find the answer? The answer is wrong. We can note the sign bit. If two positive numbers added and the result is negative number, then the result is wrong, is incorrect. Right? Because this is positive number, but the result is negative number, so the result is wrong. And this is also, this is negative number, and the sum is 0. There is a positive number, so the answer is wrong. Rules for subtraction. Choose complement. The subtract hand and add the numbers. Discard any final carrier. The result is in signed form. Repeat the example down previously, but subtract. Then, for example, 30 sub 15. 30 sub 15. Then we first use the two's complement to represent minus 15. The two's complement of 15 is 1 1 1 1 0 0 0 0 plus 1. So the two's complement is 1 1 1 1 0 0 0 1. Right? Listen. Do you know this? How to get this number? This number is the two's complement of minus 15. Because this number sub this number equals this number plus this number, right? And then we can regard this number as a number. We also can regard this number as a negative number. So the result is 0 plus 1, 1. 1 plus 0, 1. 1 plus 0, 1. 1 plus 0, 1. 1 plus 0, 1. Carry out is 1. 1 plus 0 is 0, and carry out is 1. 1 plus 1 plus 0 is 0. Carry with 1. 1 plus 1 plus 0 is 0. Carry is 1. 1 plus 1 plus 0 is 0. And carry out is 1. But this carry should be discarded. So the result is 0, 0, 0, 0, 1, 1, 1, 1. The second example is also like this. Like this. This is a minus number or negative number. We can regard the subtraction as a one number. So this number like is similar to this number plus or positive number. So positive number 17. 17 its binary number is 0, 0, 0, 1, 0, 0, 0, 1. You know, 17. Convert 17 to binary number 2, 1, 0,
0, 0, 0, 1, 0, 0, 0, 1.
0, 0, 1. So we use 8 bits to represent this number either. 1, 2, 3, 4, 5. So we should add 3 bits. So the number is 0, 0, 0, 1, 0, 0, 0, 1. You know. So the result is like either 0 plus 1, sum is 1, 0 plus 1, 1, 0 plus 1, 1, 0 plus 1, 0 plus 1, 1, 0 plus 1, 1, 0, 0, 0. The last example is also in this time, minus 1, negative 1, we use two's complement, 1, 1, 1, 1, 1, 1, 1, 1 to represent minus 1, negative 1, and plus 8, then the result is 1, 1 plus 0 is 1. 1 plus 1 is 0 and the carry is 1. So 1 plus 0 plus 1 is 0, carry is 1. 1 plus 1 plus 0 is 0, carry is 1. 1 plus 0 plus 1, carry is 0. Sum is 0 and the carry is 1. 1 plus 0 plus 1, sum is 0 and the carry is 1. This one is discard carry. So the result is 0, 0, 0, 0, 1, 1, 1. So the result is 7. Hexadecimal numbers. Hexadecimal numbers use 16 characters or use 16 symbols. 16 symbols to represent one bit, to represent one digit.
0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E.
Yes. The number 0 through 9 and the letters A through F. In hexadecimal numbers, Each bit has 16 symbols, 16 characters. Use A to represent 10. To represent the decimal number 10. Use B to represent the decimal number 11. Use C to represent the decimal number 12. Use D to represent 13. Use E to represent 14. Use F to represent 15. So, the zero corresponding binary number is 0, 0, 0, 0. And 1 binary number is 0, 0, 1. 2, 0, 0, 1, 0. 3, 0, 0, 1, 1. 4, 0, 1, 0, 0. 5, 0, 1, 0, 1. 6, 0, 1, 1, 0. 7, 0, 1, 1, 1. 8, 1, 0, 0, 0. Do you find the pattern?
Yes, sir.
How is the pattern? If we know the hexadecimal number, how to convert the decimal number to binary number? How to convert the hexadecimal number? Convert the hexadecimal number to binary number. Do you know?
Hexadecimal after that binary.
Yes. We should know that 4-bit binary number can represent 1-bit hexadecimal number. So we should know the weight of this position on binary number. The weight of this bit is 8. Do you remember? This is point, and this one binary number. The weight, the weight of this position is 2 0, right? This is 2 1. This is 2 2. This is 2 3. 2 minus 1, 2 minus 2, 2 minus 3, 2 minus 4. So the result is 8, the result is 4, the result is 2, the result is 1, the result is 1. So if we want to represent 0, the result is 0, 0, 0. And if we want to represent hexadecimal number 4, 5, hexadecimal number 5, we only use 4 plus 1 equals 5. So the binary form is 0, 1, 0, 1. This number is a hexadecimal number. And this number is 4-bit binary number. Do you know? So let's see this. 8 represent 5. 4 plus 1 equals 5. Right? This 4 plus 2. 4 plus 2 equals 6. 4 plus 2 plus 1 equals 7. 8. Right? 8. Now 8 plus 1 equals 9. 8 plus 2 equals 10. 8 plus 2 plus 1 equals 11. 8 plus 4 equals 12. 8 plus 4 plus 1 equals 13. 8 plus 4 plus 2 equals 14. 8 plus 4 plus 2 plus 1 equals 15. Okay. We should remember this 16 number. This 16 number we should remember. Okay, have a rest for 10 minutes. A large binary number can easily be converted to hexadecimal number by dividing it into 4-bit groups. Because we know 4-bit binary number can represent 1-bit hexadecimal number. And converting each into its equivalent hexadecimal character. For example, like this binary number. 0 1 0 1 0 1 0 1 1 0 0 0 0 0 1 1 1 0. This is a binary number. If we want to convert it into hexadecimal, then we first need to group the binary number by 4 bits, starting from the right. In fact, we should start from the left of the point, from this point, from this position. We should divide the number start from the point left of the pointer and from the right of the pointer. Thus, this binary number can be converted to hexadecimal because 8 plus 4 plus 2 equals 14. 14 is E, right? And 0, 0, 0, 0 represents 0, so it's 0. And 4 plus 2 is 6, so it's 6. And 8 plus 1 equals 9. So the hexadecimal number is 960E. 960E. Hexadecimal is a weighted number system. The column weights are powers of 16. Powers of 16, which increase from right to left. Column weights. 16 zeros. The first position is 16 zeros. The second is 16 1. The third is 62. The fourth is 63. So, if we want to extract 1A to F in decimal, we should start by writing the column weights. 16 is 16. 16 2 is 256. 56. And 16 3 is 4,096. 96. We should translate. We should translate. 1A2F. So the decimal is 1. F is 15. So 15 plus, times 1. 2 times 16. A represents 10. 10 times 256. And 1 times 4,096. And then plus in. So the result is 6,703. And then you can calculate this number. But 16.2. Please see the blackboard. 16 times 16. 6 times 6 is 6. 3. 1 times 6. 6 plus 3 is 96, right? And then 1 times 6, 1 times 1,
6 1.
16. So the result 6. So the result 9 plus 6 is 5. 1 plus 1 is 2. So 62 is 200 and 56. Continue to represent to multiplication. 256 times 16. 6 times 6 is 6. 5 times 6 is 36, right? 2 plus times 6, 12. 12 plus 3 is, right? And 1 6 1 6
1 5 1 2.
5 2, right?
Yes, sir.
So 6 9 0. 1 plus 2 plus 1 is 4. So 16 3 is 4,096. And then you calculate this expression. One times 4,096 plus 10 times 256, 2,560 plus 2 times 16. 2 times 16 is 32. right? Right? 2 times 16 is 32. And the last 15 times 1. 15 times 1 is 15. Right? Right? So we can first use this calculator 2. 32 plus 15, 7, 4, right? Then plus 47, right? 7, 0, 6, 2, right? Right? So the last one is plus is 6 plus 7 is 13. 13.
Okay.
9 plus 1 is 10. 1 plus 6 is 7. 4 plus 2 is 6. So the result is 6,703. So we can use this method to convert all hexadecimal numbers to decimal numbers. Octal numbers is another kind of number. Octal uses the symbols of 0 through 7 to represent numbers. 8 and 9 are not used in octal. So please see this column. This column. This is octal. 1 bit or 2 bit octal number. From 0 to 7, it is equal to decimal number. It is equal to decimal number. But from 8 to 15 in octal number, 8 is represented by 1 0. And 9 is represented by 1 1. 10 is represented by 1 2. 11 is represented by 1 3. 12 is 1 4. 13 is 1 5. 14 is 1 6. 15 is 1 7. 1 7. Why? Why? Do you know why? Because the column weight of octal number is powers of 8. Powers of 8. So we can see that. We can see that the weight, if the number is an octal number, octal number, then the weight of this position is 8 0. This position the weight of this position is weight 8 1. This position is 8 2. This position is 8 3. And this position 8 minus 1, 8 minus 2, 8 minus 3, 8 minus 4, 8 minus 4. So one bit if we want to represent 8, we should use 1 0. 1 0 to represent 8. 0 0 1 0. Because the weight of this position is 8. And then and 9 8 plus 1. This is 1 8 right minus 8 3. This is the weight. This is the weight. So 9 equals 8 plus 1. 8 plus 1. 8 plus 1. So the 8 number, the octal number of 9 is 0 0 1 1. 0 0 1 1. And 10. The decimal number 10. Decimal number 10 is equals 8 plus 2. Right? 8 plus 2. So the octal number is 1 2. Is 1 2. 1 2. Like this manner. 11. 11 is 1 3. 12 is 1 4. 13 is 1 5. Right? 13. This number is decimal number. This is decimal number. This is octal number. And 14, decimal number 14 is 1 6. 1 6. And 15 is 1 7. 1 7. The key numbers is binary numbers, octal, binary numbers and hexadecimal numbers. We should understand. We should pay attention to these two numbers. But octal numbers, we only need to know. A binary number can easily be converted to octal number by grouping bits 3 at a time and writing the equivalent octal character for each group. 3 bits y. 3 bits y. Because one octal number bit can represent 3-bit binary number. For them. One octal number. Octal binary. 0. Right? 2 1 1. 0 0 1. 2 0 0. Right? 3 0 1 1. 4 1 0 0. 5 1 0 1. 1 1 0. 7
1 1
7
1 1
1 1 1. You know 2 plus 1 equals 3, right? 4 plus 1 equals 5. 4 plus 2 equals 6. 4 plus 2 plus 1 equals 7. So we can use one octal bit to represent the 3 binary bits expressed in octal. Then we group the number 3 at a time. 3 at a time. So 2 plus 1 4 plus 2 equals 6. 6 1 0 3 1 1. We can add 2 zeros to the left.
Okay. 1 1 3 0 1 6.
Yes.
So 1 1 3 0 1 6.
Yes. Yes. This is the answer. The column weight of 8 of octal numbers is this 8 0, 8 1, 8 2, 8 3. So if we want to convert an octal number to decimal number, we can use the column weights like this. For example, 3702. It is an octal number. If we want to convert this number to decimal number, we can use this. 3 times 512 plus 7 times 64 plus 0 times 8 and plus 2 times 1. 2 times 1. So the result times 3 6 3 13, right? 7 times 16 64. 4 times 7 is 28. 28 and 6 times 7 is 42. 42 plus 2. 42 plus 2 is right? 4 times 7 is 28. 28, the carry is 2. 6 times 7 is 42. 42 plus 2, 44. And 0 times 8 is 0. 2 times 1 is 2. So the result is 2. Right? This number plus this number. So 6, 8, 9, 1. So the result, right? The result because the decimal number is 1986. And say in this section, we will learn another kind of code, not numbers, code. We have learned decimal numbers, binary numbers, hexadecimal numbers, and octal numbers. The important is binary numbers and hexadecimal numbers. Now we will learn another kind of code, BCD, binary coded decimal. Binary coded decimal is a weighted code that is commonly used in digital systems, such as clock displays, where it is necessary to show decimal numbers. In BCD, we use 4 bits of binary number to represent 1 bit of decimal number. 1 bit of decimal number. For example, we use 0, 0, 0 to represent 0, and we use 1, 0, 0, 1 to represent 9. But we use 0, 0, 0, 1, 0, 0, 0 to represent 10. Because there are 2 decimal bits. We only use 4 binary bits to represent 1 decimal bit. So we should note that. The table illustrates the difference between the strict binary and BCD. BCD represents each decimal digit with a 4-bit code. Notice that the codes 1010 through 1111 are not used in BCD. You can think of BCD in terms of column weights in groups of 4 bits. For an 8-bit BCD number, the column weights are 8-bit BCD number are 80, 40, 20, 10, 8, 4, 2, 1. For example, what are the column weights for the BCD number? For the BCD number, 1 0 0 0 0 0 1 1 0 1 0 1 0 1 we should know that. How to translate this BCD number to decimal number? It is complex. We should 1 plus 8. 8 plus 1 is 9. 8 plus 1 is 9. And this is 10. This is 10. 10. This is 40. The weight of this position is 40. And this is 40, 80, 100, 200, 400, 800, 1,000, 2,000, 4,000, 8,000, 8,000. So it represents decimal is plus. But we should know that BCD is not used to represent numbers. It is not used to represent numbers. So we don't need to convert this number to decimal number. We don't need to. We only use 4 bits to represent one decimal number. It is a code, not a number. We don't need to compare the numbers. Gray code is another kind of code. Gray code is an unweighted code that has a single bit change between one code word and the next in a sequence. Gray code is used to avoid problems in systems where an error can occur if more than one bit changes at a time. So we use bit-binding pattern. The nearby two numbers, only one bit are different. For example, the first and the second, only the last bit is different. And the second number and the third number, only the second bit are different. The third and the fourth number, only the first number are different. The first bit are different, and the fourth number and five number, only these bits are different. This number and this number, only these are different. The two numbers, only these bits are different. The two numbers, only these are different. The two numbers, only these are different. The two numbers, only these are different. These two numbers, only these. 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 This is the pattern of the gray code. It is used to avoid problems in transmitting systems, in communication systems. Ask2 is third kind of code for alphanumeric characters and control characters. In this original form, ASCII encoded 128 characters and symbols using 7 bits. The first 32 characters are control characters that are based on obsolete teletype requirements. So these characters are generally assigned to other functions in modern usage. ASCII 2. In 1981, IBM introduced extended ASCII, which is on 8-bit code, and increased the character set to 2056. Other extended sets have been introduced to handle characters in languages other than English. The parity method is a method of error detection for sample transmission errors involving 1 bit. A parity bit is an extra bit attached to a group of bits for force the number of ones to be either even or odd. The ASCII 2 character for A is 11000001, and for capital A is 10000001. So the ASCII A has an odd number of bits that are equal to 1. Therefore, the parity bit is 0. Because small a has three one. We use 0. The ASCII capital A has an even number of bits because he has two one. So the parity bit is 1. Okay, we have learned this chapter 2. And the key terms include byte of group of 8 bits, 8 binary bits. 8 binary bits, we call this byte, 1 byte. Floating point number or number representation based on scientific notation, in which the number consists of an exponent and an mantissa. Hexadecimal, a number system with a base of 16. Octal, a number system with a base of 8. BCD, binary coded decimal or digital code, in which each of the decimal digits 0 through 9 is represented by a group of 4 binary bits of 4 bits. Alphanumeric, consisting of numerous letters and other characters. Alphanumeric, for example, hexadecimal, 1 bit hexadecimal number, from 0 through 9, and A through F. So this is called alphanumeric. ASCII 2, American Standard Code for information interchange, the most widely used alphanumeric code. Parity in relation to binary code. The condition of evenness or oddness in the number of ones in a code group. If the number has even ones, then the parity of this number is 0. If the number has odd ones, then the parity is 1. Cyclic redundance check for type of error detection code. Question. There are 4 questions. 10 questions. For the binary number 1000, the weight of the column with the 1 is C.
8.
Yes, 8. The answer is C. Second, the 2's complement of 1000 is 2's complement.
For 1000. The first one this is B versus 1000.
1000.
This same not change.
The answer is B.
Yes, but my answer is also B.
Yes. 2's complement.
Yes.
2's complement. We first need to find the 1's complement.
After this,
Right?
yes. The same as
Into 100. The 1's complement.
0 1 1 1.
0 1 1 1, and then plus 1. Then plus 1. So 1 1 0 1 1 0
0
1 0 1 1.
Same.
So the good complement of is B.
Yes.
3 questions. The fraction of binary number 0.11 has a decimal value of
this is 0.75. That means 3 by 4. C. Yeah. 0.75.
Vincent.
Maybe C.
Okay. So the weight of this position is
0.75 or
2 minus 1.
Yeah.
Right? And
0.5.
this 2 minus is 2. So the first is 1 over 2 plus 1 over 4.
So 3 by 4.
Yes. The answer is C.
Yes.
The fourth question. Hexadecimal number 2C has a decimal equivalent value of
44. B. 2C. This is 44.
44.
Yes.
2 plus 6. Right?
Is 44.
2 plus 6. The weight of this position is 60 grams. This is 61. So the expression is 2 times 16 plus C. C is
12.
10,
12.
11, 12,
Yes.
12. Right? So the result
32
is
plus 12 equals 44.
32 plus 12, So the answer is 44. Right? Just assume that the floating point number is represented in binary. If the sign bit is 1,
Negative number.
yes,
It's negative.
yes, the number is negative. When two positive sign numbers are added, the result may be larger than the size of the original numbers, creating overflow. This condition is indicated by
A change in the sign bit A. A change in the sign bit.
a change in the sign bit. Yeah,
A.
the answer is A. 7. The number 1010 in this D is equal to decimal number
1010.
but the decimal number 10. 8 plus 2, right? 8 plus 2 equals 10. Right? The weight of this is 1. The weight of this is 2. Of this is
0.
10. 4. This is 8. So the
8
number
plus
8 plus 2
It's 10.
is 10. So the answer is B. Only example of an unweighted code is
Very good.
yes, Greek code. Only example of alphanumeric code is
ASCII 2.
yes, ASCII 2. And all example of an error detection method for transmitted data is the
Parity check and also CLC. This both.
Yes.
ASCII.
both A and B, both of them are. Okay, class is over. 下课。
谢谢。